And welcome back. Now today we're going to be addressing a subject that's slightly off-piste when it comes to Arduino world, but this kit you see in front of you here is in fact destined to be used with an Arduino project that I've been going along, but it's not actually an Arduino project in itself. What do I mean by this? Okay, let's make things very clear. This is a signal or function generator kit. Okay, as you can see, it's got lots of parts and it's even got a little tiny board and things. And the idea is that I'm going to make a very cheap and simple signal generator module, basically. So when this is all built up, it will generate sine waves, square waves, and triangle waves, but not sawtooth. And why do I need that? Well, just apart from general electronics type work that I play about with, I thought this would be a good kit to try out some of the debounce circuits I've played about with our rotary control or rotary encoder a week or two back. However, that's sort of almost to one side really. This kit as a whole costs just under £10, very simple to set up. I was a little bit concerned perhaps for the cheapness. I thought, what is it they're giving me here? Are they giving me a 555 timer, for example, which we can create quite a lot of waves, you know, square waves and triangle waves and so forth. But I needn't have worried, because when I got the instructions out, if you look at the circuit diagram on the back, the first thing that struck me, that bit down there, I'm just zooming in on, it says it's an XR2206 Okay, that bit there. So what's an XR2206 module when it's at home? Well, for that we need to go over to the browser and find out a little bit more. Right, so this is the PDF for that particular chip, and straight away I can see that, yes, this is okay, because it says down here, look, the XR2206 blah blah, it's a monolithic function generator. Incidentally, yeah, they tend to call these sort of items function generators, not signal generators. Signal generators, I guess, are now reserved for like a simple 1 kilohertz sine wave generator. That's a signal generator. This and everything else in the world is a function generator now, because you can generate all sorts of different waves and waveforms and program them in and all sorts of things. I'll have to show you my proper signal generator in a future video, but for now we're going to concentrate on this, because this is easily within hobbyist type price range, as I say, under £10, and because it does use this particular chip, I'm thinking, that's going to produce a proper sine wave, not something cobbled together out of a square wave. So this is the data sheet for it. It's not worth going through it at the moment. It does tell you all the parameters, ins and outs, and the amplitudes and triangles. Okay, fine, enough. Let's just say that it will generate a sine wave, a square wave, and a triangle wave properly. Okay. Now, I can already hear some people saying in the background that, Ralph, hang on, won't the Arduino generate at least a square wave? Well, yes, it will. And therefore, if it generates a square wave, can't we then generate a sine wave out of that? Well, yeah, yes, you could. Let's just have a look at what Arduino say about this whole thing. Okay, so going over to Arduino, it says the Arduino Dewey, which is an ARM-based Arduino board, one of the first, I think, not one of the first. Oh, it is the first Arduino. Okay, fine. It says somewhere in here, let me just slip over to this one. Simple waveform generator with Arduino Dewey. Okay, fine. So this is from the Arduino CC website. It says all you need, yeah, bear that in mind, is an Arduino Dewey. I haven't got one, can't afford one. Plus a simple little circuit. So there's the, well, that's what it gives out. Look, that's great. And you have a little circuit here, and yeah, and then you tell it what sort of waveforms you want. So, okay, let's not dismiss this out of hand, because you've got to describe what your sine wave looks like and describe the triangle and sawtooth and square wave and everything else. You could then obviously describe a bespoke wave. It'd be a lot of work though typing all these in, but you could do it. But for me, The biggest hurdle in this is the fact you do need an Arduino Due. As I say, I haven't even got one. One, because I don't really need a 32-bit microcontroller for much, and if I did, then I've got the ESP32 to play about with. And secondly, well, let's go over to AliExpress, which is, if you've never used AliExpress, it's obviously a Far Eastern Chinese based warehouse, but what it is, it's almost like an eBay for components. So it sources components from their sellers, and they have, you know, thousands and thousands of sellers, and they all compete against one against the other. But AliExpress basically takes a commission and I don't know, well, organises the whole thing like eBay does. So if we go over there, because that's the best place you're going to be able to compare prices. Now, £9.84 for a Dewey R3 board. Now, of course, it's not a real one, it's a clone. Nothing wrong with that. It is, after all, an open source hardware system, so they can clone it, fine. Moving down that list, what else? There's another one there for £10.21, another one for £9.88. So you can see they're around about the £10 mark. Okay, that's an Uno, that doesn't come into it. So £10 for a Dewey, plus the programming effort, plus the fact you've got to put in a box. Okay, now what if you thought, well, I don't want to use AliExpress, I'd rather use something a bit more local. I did a quick search on Google just to find out what my local price might be, for example, and here's the search. And as you can see, they're all around about the £30 mark, which is a significant amount of money, isn't it? Yeah. So, well, even in fact, there's one there from Amazon. Amazon's probably going to be one of the more keenly priced ones. How much are they doing it for? This is the UK version, certainly, of Amazon. Well, $34.99. Okay, not for me then. That's too much. One of the clone ones, I could say, yeah, £10 for one of these. Okay, but then I've got to say, why bother? When you can get this entire kit here for tenner with that chip in that does everything, I think sometimes, you know, we must step back in the Arduino world, and just because you've got a hammer, not everything needs to look like a nail. Okay, so although, yes, I'd love to make something on the Arduino Uno here that does the same as this, frankly, well, the Uno can't do it anyway because it hasn't got a digital to analog output, but the Dewey has, and I think the Teensy might have, but even so, this is bespoke hardware, isn't it? It's designed to generate those signals, so that's what I'm going to build. Okay, so I'm going to knock all this up. Show you the finished product. I'll take a few photographs along the way. I'll just empty this bag out so we have a better idea of what's in here. Right, what do they give us here? Oh, there's a little jumper over there trying to escape. Capacitors, potentiometers, all of that do actually give you the three knobs and, well, a few bits and pieces really. And of course the the laser cut sort of acrylic shell. Where did I get it from? Well, I actually bought it from KK Moon on eBay UK, but as lots of feedback from that buyer, from that seller indicates, they actually order it via Amazon. That means they probably got a shop on Amazon, you know, an Amazon storefront, and they just put their orders via that. So here it is. So that's the KK Moon XR2206 $7.99. So in fact it's less than a ton of what I said, wasn't it? Less than. And prime, so I can get it tomorrow. Well, I've already got it now, so I don't need another one. And well, as you can see what it looks like here, very nice. Acrylic shell, three potentiometers for, it says here, frequency range, adjustable frequency and amplitude. Great, want that. High resolution, so one of them probably selects the actual waveform you want. I don't know yet. We're going to put it together. Okay, and then we're going to actually put this through a little Schmitt trigger that I knocked together for testing out the rotary encoder and just see how well it copes with that. I need an oscilloscope with that, of course, but luckily there's one down in the workshop. Okay, that's all I'm going to talk about for the moment until this is all built up. For those of you who resist sort of building projects like this because they go, oh, my soldering skills, I'm not really sure. don't be hesitant in doing it. These sort of boards are very easy to solder because they're all pre-tinned and everything. And if you're really that worried about your soldering skills, make sure you've got a proper iron, an Antex 15 watt or something like that, probably a Model C or CN, and get some strip board and just play about with it. Just solder some rubbish resistors on it or something like that, and you'll soon get the hang of it. That means you can build stuff like this, and you'll have a little, when this is all built up, this will be a useful little thing to have in your toolkit, and you might only use it 2 or 3 times a year, but for, what was it, $7.99? Yeah, I think it's probably worth it. Okay, enough chat, let's go on and build it. Right, I'm not going to walk you through every single step. I mean, it's pretty simple stuff, but here's some components laid out on the bench. Here it is, partly assembled, just a few, and well, as you can see, it's building its way up slowly, and it's pretty easy to do. There's the finished product. Nice. So here's the final product, not yet put in its case, and unfortunately upside down on this video, but that's because I've got it lashed up to my oscilloscope just to see what it was like. And the little tiny JYE one as well, actually. So they're up here. There's my oscilloscope plus the little one. Let's make it a little bit better. There we are. Look. So the Rigol on the right is obviously the digital storage scope that costs about I don't know, 100 times more than the little one on the left that we had a little kit video on not so long ago. And I just thought this would be a good idea to try it out. Now currently I'm transmitting from that signal generator something like 100 kilohertz. If we just zoom right in, there we are, 101 kilohertz, a sine wave, and the little one here, JYE, is not bad at all. That's saying it's 101, but I mean, for what it is, I think it's doing pretty well actually. So sine waves, okay, 100 kHz. Let me go back to the square wave generation. There's something a little bit dodgy about square wave, but at least the sine wave at 100k works. It should go up to whole megahertz actually. We'll come back to this though. I want to go back to this square wave, so back in just a jiffy. Right, so I've switched it to the square wave, and this is 100 kilohertz as well. I haven't really touched the frequency, and as you can see, it's, well, square-ish. I'm not quite sure how useful that's going to be for logic circuits. Well, no, to be fair, it probably is usable. I mean, there is a pulse, isn't it? It goes higher, then comes low again. So that's not too bad. But interestingly enough, the little tiny JYE here is also keeping up rather well. That's not bad at all. Okay, now I'm going to bring down the frequency a little bit anyway, just see how it... so on the right, it's saying 94, 92. There's not much control over each range. So if I turn that one, oh no, it moved a little bit. So we're down to 81, which is the minimum I can go by. But as you can see, okay, the JYE is going a bit mad. I don't think I can keep up at that. Let's change the time base for it. There we are. That's as low as it will go on the JYE. But still not a very good square wave, is it? Okay, let's take the frequency down quite a bit. Say bring it down to almost audio frequency and just see what the square wave looks like then. Right, here we are now at 227 Hertz, it says on the Rigol, at 245 on the JYE, but that square wave is not square, even at this frequency. Now it should be, and in fact it was when I was testing this out. So something's gone awry, and I'm not quite sure what it is. So I'm going to play about and see if I can get that square wave back again. Right, well I didn't actually have to do very much. I had to adjust the... Well, it says it's amplitude, but that should have absolutely no effect for square wave because it's on a separate output. But I'm guessing there's some kind of interaction between the controls. So that's a square wave at 227 or thereabouts. And both scopes are doing pretty well, I think, really. Okay, time to up the frequency again. So let me adjust it here. So this is a 100 kHz square wave. It's not looking too bad. Well, not looking too bad over here. Not looking so good on the JYE, but then when I did the review I said you can't expect that much from a little tiny thing like this. Really this is meant more for sort of audio range, maybe up to 50k, something like that. Although it did pretty well on the sine wave, which we're going to go back to in a minute. Now that's okay, I would say. 100 kilohertz nominal. We can bring it up a little bit higher because it will go all the way up to 1 megahertz. So it's 300. I'll concentrate on the Rigel now because obviously the JUIE just can't cope. So let's change the time base so we can see exactly what it's looking like. Not much of a square wave anymore, but it still might be usable actually. Still might be usable. Oh, well, that's the maximum it will do is 1.26 megahertz, but that's not really a square wave, is it? Let me bring that back down to 1 megahertz. I think the adjustment I've got here is not brilliant. But we'll talk more about that in a minute. Okay, well that's the 1 megahertz range, and that's the signal you're getting. A sort of a, well, it's a sort of a triangle, isn't it, with a bit of a smooth. Yeah. Okay, well let's go back to the other modes, and this is square wave, always the most difficult wave to generate really. And let's see what triangle looks like. So here we have the triangle wave being generated at, what's that, 500 hertz nearly, yeah, and that's absolutely fine. Although I notice the amplitude control on the module now, instead of changing that amplitude, look what it does to it. It oh dear, it clips it at the top there, look, quite dramatically, and starts turning it back into some sort of square wave. That's not what we want at all, is it? So clipping is definitely a no-no. So let's bring that back down again. There we are, nice square wave. Right, let's sorry, sawtooth. No, it's not a sawtooth, it's a triangle wave. You can't do sawtooth on this one. Right, let's increase the frequency to something a bit more usable, perhaps 800 kilohertz going up. Oh, change the old time base a little bit. Right, that's 4 kilohertz. Yeah, that's the maximum on that particular range. I have to move the jumper over in a minute. And of course, this poor little thing is going mad. So let's adjust this as well. And we want that set to about 100 microseconds. There we are. Not quite as stable as I'd hoped, but never mind. Right, let's change the jumper. Right, so now it's saying it is 83 kilohertz. Okay, fine. Let's adjust the time base over here as well. Bring it down to 10 microseconds. Well, I can only go down to 20 on this one, so it's never going to be quite spread out, that signal. But that's fine there. Look, that's coming up to 100k, isn't it? It's not bad at all. Okay, well, I think we've sort of established that for the money, this little module is, you know, not too bad. There's a couple of things wrong with it, which I'll mention in a minute when I go back up to the video room. Now, of course, if we did want a slightly better signal, well, I say slightly better, a signal many times better, then you really would have to use something like this. This is a proper digital signal generator. You can generate any kind of signal wave you want, everything you can think of. This is what I would tend to use if I was doing anything serious. That little one that I've just put together, I can use that for little things, a bit like that scope, you know, for quick things on the desk. But I'll be doing a video probably on this one a little bit sometime later, but that's another story entirely. Now this is interesting actually. I'm running at 11.7 volts at the moment, and as you can see back here, the triangle wave is nice and steady. As I bring up the voltage though to about 12, 12.2, 12.4, look, we're getting jitter now. So if I bring it up to something like 14 volts, oh dear, look at this. And the signal's all over the place. And on the internet, stories are rife that the chip on the actual board, so that chip, when it gets into focus there, where it says 2206, they're saying that could indeed be a clone chip, or counterfeit depending on your terminology, because that should work up to 26 volts. So, on the other hand though, realistically speaking, I mean, alright, that's jittering all over the place. If I bring it back down to 9 volts, yeah, so that's 9.2 now, steady as a rock. Difficult to see, because put the light back on. There we are. So 9.2 volts input supply, and it gives us a nice steady output on both those oscilloscopes. So there we are. So there we are indeed. Now what I've got here now is the completed, put together in a box, although we'll have a chat about that in a sec. My little Schmitt trigger. What's a Schmitt trigger, you ask? Okay, we'll come on to that. And just my board here so I can connect a few things up. The Arduino at the back there, although it's got a sketch on it that I want to feed this into it eventually, is only there at the moment to supply the power to this little Schmitt trigger. Okay, first things first then. Okay, this is in a box. Would I personally put this into a box like this, knowing what I know about this now? No, I wouldn't. There's a few amendments to this layout that we need to do if you wanted to keep it for real, I think, basically. And I had a quick look on the internet since constructing it. In fact, there's two videos. One showing you how to make it, so I don't know why I made that video really, but another one showing you all the differences you can put on here. And in fact, even in my setup, my components, these two, which is the coarse and fine adjustment for the frequency, they're both 50k, which is totally wrong. What you really want is 100k and maybe a 2k or something like that to get the fine control. And in fact, one of the amendments that this chap says in his video, I'll put a link on the video description, is in fact to wire these up differently in parallel, which requires a certain understanding of what all the tracks underneath mean. But if you know anything about electronics at all, it's an easy fix. Plus the output resistor, this R1 that I'm sort of pointing to here. Where's my pointer? Here it is. I can't go right to it. This one here, stuck to the board as well. But that furthest one there, that's R1. Now that's a pull-up resistor, and it's too low. It doesn't actually follow the the reference circuit diagram by the manufacturers of that chip. And of course, as we now know, that chip is not a kosher chip either. It's what would you call it? Counterfeit's a bit strong, really. It's sort of a clone chip that doesn't quite perform as well as the original. It's a pity, really. They didn't just call it something else with another number or a suffix on the end just to differentiate it, because no commercial organisation could buy those chips in here and use them for anything, apart from which they're obsolete now anyway. So that's probably why somebody's jumped on the bandwagon and manufactured these clones. Anyway, all that notwithstanding, the output from here, as you can see at the moment, I'm displaying a triangle wave, as you saw downstairs in the workshop. That's all very good. The frequency is sort of unimportant really, because we are going to be using this eventually, not today, but eventually as part of the rotary encoder for the video. It's at 22 kilohertz, where you're never going to turn any kind of rotary encoder fast enough to get 22 kilohertz. Although some motors will, of course. If you're spinning up a motor at 10,000 RPM, then you can get quite a few pulses. We're not really bothered with that today. What we are bothered with is this Schmitt trigger. Now this I just knocked up in a few minutes, just off the top of my head really, because I didn't really follow any pattern apart from the suggestion in the data sheet for it. Now that's a CD1493. You could argue, well, it's totally the wrong chip for what I want to do, except that it is a Schmitt trigger. A Schmitt trigger will switch, as the name implies, although it's a person's name, Schmitt. It switches at a particular point and then doesn't switch back again until another particular point. So if I draw this out, you'll get a much better idea of what Schmitt trigger does. Okay, so let's assume then we have our triangle wave as we do there. So nice triangle, that's all it's doing, right? We're assuming a 50% duty cycle, even though I've drawn one bigger than here. Let's just ignore that. What a Schmitt trigger will do is say, I'm detecting some kind of voltage, but I'm not switching. I'm switching at this point here, and I don't care what happens going up. Now I'm coming down, but I'm not switching back yet. The lower point has now been reached. I'm switching back again. So what you actually get is the output is a switch here, then across, then down. And the reason it's all a bit cack-handed on this video is because I'm watching the monitor as I'm doing it. So you can see we're getting a little square wave, and then exactly the same thing happens up here. It'll switch at that point, ignore the best of it, and switch off like that. So what this does is give you a square wave out of this triangle wave. All well and good, fine. That's what we expect from a Schmitt trigger. But what I'm hoping, of course, is that with a rotary encoder, and I can't prove this today, but I will do, if we have a nice square wave coming out like that from our AB pin, then what we might end up here is some little tiny pulses like this, Well, they might even go up to there for all I know. And this sort of range here, this time range, in fact, is very short. In fact, the data sheet says something like 5 milliseconds. All right, so these little pulses at the end here, I'm hoping that this Schmitt trigger will go, no, I can't do anything with these, I'll just ignore them until the next actual pulse comes in. All right, so it should clean it up. But what we're here to prove today is that this little circuit I've knocked together, I'll show you the data sheet for that, for this particular chip, but it's not the chip I'd choose if I had different ones, but I just happen to have one of these in my box, so there we are. Right, let's go over to the browser window. So this is a 4093B, but we wouldn't use this normally, because if you notice on this bit of the diagram here, you can see that each one of these, well, down here actually is better. Look, you've got two inputs to this NOT gate. In fact, it's a NAND gate. And the reason you know it's a NAND gate is because you've got this little circle at the end of it. So what this says is when both these are high, the output will go low, and vice versa. When both these are low, this will go high. Now, okay, well and good, we can just join these inputs together effectively to create a single input NAND gate. But imagine if we connected that up then to this circuit. The rotary encoder would go high or low, and the output would go low or high. That would confuse the hell out of everybody, quite frankly. So what I've actually done is put two of these in series. And the actual circuit diagram I sort of followed. It's right down the bottom here somewhere. Let me find it and get back to you. Right, this is it here. So this is sort of a switch bounce thing. Let me make that a little bit bigger and zoom in on it. Bigger still. Yeah. Oh, hang on. Right. Okay. That's big enough. So what you can see here is that we've just joined the two inputs together, and it says put a 120k high to VDD, which we're using as 5 volts because it's powered from the Arduino, and have a capacitor less than or equal to 0.001, which is let me see, that'd be 1 nanofarad or less. Sounds very low, I've got to admit, it does sound low. And there's your switch. Okay, so this would be either a push switch, button, whatever, toggle switch, or in our case a rotary encoder. So as you shut this and make it connect this input to ground, the output goes high, and when you release, the output will go low. Now what we want is the reverse of that, because this is inverting the state of this. So I just put one here and then one of these exactly the same like that after it. Okay, without this gubbins, just this bit here, put another one after it, and that's how you'd get rid of the inversion, which we don't want. And because coincidentally there were 4 of these in that one chip, I used 2 per pin AB for the rotary encoder. If all that sounds a little bit what you're talking about, Ralph, all will be made clear when I do that next video about rotary encoders sometime down the line. But now, today, we just want to check that it's going to change this triangle wave into something a bit more resembling what you'd say comes out of a rotary encoder. And if you can do that, then of course it can do anything we want. So let me switch back to the workbench. Right, so at the moment I've got the mini scope here connected up directly to the output via this gubbins here to this one here, triangle. So I'm going to disconnect that and then connect it to the output, which is this one over here. And there we are. Now you can see straight away that the frequency hasn't changed. It's still just about 21.9, and we have, well, a passing resemblance, I think, more than a passing resemblance to a decent square wave. And the duty cycle, it says here, is 80%. Now what was it previously? That might be quite interesting, wouldn't it? See what the duty cycle has changed from. What does it say there? 39% or 40. So that should have been, well, if it had inverted, it would have been 60%. So it's interesting that it's gone up, hasn't it? Wonder why. You'd think it'd be doing pretty much the same, unless, of course, one of these controls has anything to do with it. Let's have a look. So we've got a 22 kHz, 80%. If I reduce the... Oh, look, I mean, reducing the amplitude by turning this red knob here, and the duty cycle is actually going down. Interesting. Not quite sure. That's as low as I can get it. Not sure why. I still have my doubts about that amplitude knob. Anyway, that's an aside, isn't it? Okay, so what we've got then is a pretty good square wave. Not perfect, but I think half the problem there is probably this, or it could be that. This capacitor changes it a little bit. The triangle wave, that is. But anyway, the fact that it can turn a triangle wave into a square wave like this, because the Schmitt trigger turns on part way through the cycle, as we said, and shuts off again, that's good. That's exactly what we want. So when we do feed in a proper square wave with bits on the end of it, so if you can imagine this is our rotary encoder giving a pulse from the A pin, say, and then it does some dodgy business at this end here for a very short fraction of time, I'm hoping that Schmitt trigger will just ignore that and not give us any bounce. Now I've disconnected something. Look. Well, talking of disconnection, I think it's time we called a halt to this. I think we've proven that this kit's okay with a few little amendments. I'll put the link to the video where this chat goes on about it. But I think this kit, once it's got a couple of little things sorted, I think it's all right for the money. I mean, 7-8 quid or whatever it was. I mean, the chip itself, if it's a kosher one, it cost you £5. So not that you can get them anymore, not in the UK anyway. You can just probably get the clone ones. It's okay. As I'm using it here, as I'm using it here, as I'm using this little oscilloscope. For the little things on the desk like this, I think it's it's okay really. If you want bigger and better, well, you saw a very brief glimpse of my proper signal generator, and one that I'm hoping to use to test this out properly with a programmable signal, so I can give it a square wave with a little bit of jitter at the end. Seem to have a loose connection here, don't we? Because that square wave keeps going off. Anyway, that's it. That's enough. I think that's a pretty good, a pretty good test of the Schmitt trigger there. That's working. We'll use that going forward. Although, as I say, next time I'll give you better details of a better Schmitt trigger, just to show you what I mean. And we'll be using some rotary encoders with any luck, with optical outputs, so they won't have any jitter whatsoever when we compare the difference. Okay, that's it then. Enough for today. I've done my soldering stint, I think, for the week. And I hope you enjoyed it and, well, maybe even learned something as well. Great, thanks very much for watching and see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.